Okay, what we're going to talk about today are some early models of the atom. Okay. In the late 1800s, kind of up through the 1890s, the typical model of an atom was what they called a plum pudding model. Basically, what this model said is we had kind of a sphere of positively charged material, and it had some tiny negatively charged electrons in it. So most of this is positively charged, but inside it we've got little bitty things, little bitty electrons that are in there. Okay, so kind of the whole idea of the electron or the atom, and they did talk about the atom. They did talk about protons and electrons, things with positive charges and negative charges, but their whole thought was it was all together, one big massive thing, and they were all mixed together. Called plum pudding because this would be a pudding with a bunch of little bits in it. So around 1911, Ernest Rutherford started doing some experiments here. And in his experiment, he had a radiation source, and this source basically spit out alpha particles. An alpha particle is just a hydrogen atom, or not hydrogen, helium atom with all the electrons removed. It's the nucleus of a helium atom. So 2 protons and 2 neutrons. Or at least we know that that's the case now. Ernest Rutherford didn't. He just knew it was an alpha particle. Okay. So what he did was he shot this at a piece of, I believe, gold foil. Let me look that up before I say it. I didn't put it in my notes. I just drew the picture. But I believe it was a gold foil. Okay, it's not where I thought it might be. So yeah, but it was a piece of metal foil, and what he noticed happening was, and around this foil, he put a screen that kind of went all the way around it that would detect when the particles hit. So the particles hit here, and what happened is that a lot of it got scattered. Okay. And this alpha particle gets scattered if there are only positive charges, which is what we have here. Okay. If it was neutral, it would go right on through. And so kind of what he realized then is there was not an even mixture of positive and negative charges in the atom like this, that somehow the positive and the negatives were separated out at different spots. And so he came up with what was called the planetary model. And they call it the Rutherford model as well. Where we have a positive nucleus with electrons orbiting around it, and mostly empty space between. Okay, in this model, it's just like with planets, except if you add energy, instead of adding gravitational potential energy and moving something to a farther distance away, what you're adding here is, if you add light, then it can raise the electron up to a higher orbit level. So absorbing energy means the electron moves to a higher level. Okay. Just like if we do work, we add potential energy to an object, that means we're raising it higher up gravitationally. Okay. What this also means is if an electron moves to a lower orbit, it must give off energy. Okay, so again, I'll use the analogy from gravity. If we have something that's up high and it goes down like that, it starts with this amount of potential energy. The potential energy goes away as it's falling. It's got to go to something. Now, as it's falling, and we're talking about large objects with gravity, it gains kinetic energy. Okay. If we're talking about an electron being pulled towards a proton, what we're talking about there is an electron gives off light. Going to a lower level. Okay, so that was the Rutherford model, and the reason we're talking about this older model, and we've kind of moved beyond it, is in many ways we often depict it like that. We depict it as a proton with an electron orbiting around it. Okay. Now, the distances are not even close to being in scale. It's if we were to put the right size for a proton here in the nucleus, the distance between that and the orbit, if we want to call that of the electron, it'd be 10 to the 5th about meters, or 10 to the 5th times bigger. So we're talking about 100,000 times the size of this. That's the orbit here. So when he said a lot of empty space between, he means a lot of empty space in between. The nucleus is very, very small, about 10 to the minus 15th meters. The size of this first orbit is about 10 to the minus 10th meters. Okay, so a whole lot of empty space in between. Okay, so here was kind of our first more advanced model of the atom. It's called the Rutherford model. But as I started doing experiments, what they found was that the energy of the light only seemed to be given off from an atom in very specific wavelengths. And so, and the wavelength ended up being following kind of this equation, 1 over n prime minus 1 over N2. So basically it's the difference between energy levels here, where N is N prime plus 1. Let me write that again. N prime plus 2, N prime plus 3. Basically, what we're talking about is whatever our starting point was, being able to go up one energy level higher. And I think I've kind of written this a little bit wrong. Where did it go? Where did it go? I've got this wrong. Basically, these are two different N numbers when we're going from one N number to another. Our lowest level is where N is 1. And so our energies would be going back to N1 here, and then the next level would be where N is 2. Okay. So our lowest level is N is 1, N is 2 is the next, N is 3. So what they call the Lyman series are wavelengths of light where you're going from higher energy levels down to 1. Okay. In other words, we're going from level 2 down to 1, or level 3 down to 1, or level 4 down to 1, or so forth. All of them going down to 1. And what they give off is this certain wavelength of light. So that would be what they would call the Lyman series, the Balmer series. And I have never seen them ask questions with these names on them in particular. It's going from higher levels down to 2. Oh, sorry. To level 2. So it goes from level 3 down to 2, level 4 down to 2, level 5 down to 2. And so we started seeing that energy only gave off, or light was only given off in certain wavelengths from an atom. It was not what the planetary model said, because with the planetary model, you can take this electron, raise it to a higher level, and have it fall kind of anywhere. You know, if I raised it up right here and let it drop, okay, it'd give off a certain wavelength. If I raised it up here, it'd give a different one. But I could put it anywhere, just like a planet. I could take a planet and move it at any distance from a star. Okay, and so what we're finding was that it would only give off certain levels of light. So at that point, they're realizing that, well, there's something else going on. It's not just our planetary model here. And in 1912, Niels Bohr studied in Rutherford's lab. And he was doing work with that. He was convinced that Rutherford's model had some validity, but it needed to incorporate the quantum theory of light. So we talked about the quantum theory, that light could only have certain wavelengths, and so he came up with, or put together, a new model that incorporated that. And basically what his model said was that the energy of light is basically the difference between two levels. And I'm going to put an L subscript here for the lowest level, where n would be some number above that. So if I'm drawing the energy levels, here would be E sub n, here would be E sub L, and as the electron fell from there to there, if n is 1, this would give off a quantum of light with energy HF. Okay, but here now our letter N is integers. Okay, so there were only specific levels that this would work at. So from our highest to our lowest energy, or from our next level to our lowest, we had HF is equal to E2 minus E1, where E1 is the minimum energy state. At the smallest radius. And it's called the Bohr radius. Okay. And we only have a few minutes, so let me glance at this next one and see if we've got some time to. Okay. All right. So, actually, I think what we've got here is a chart, or a diagram, that shows the energy level. That n equals 1 level, where the electron would be at the Bohr radius. They also call it, at the ground state, the lowest energy level. We can go up to the next highest level here, level 2, and as it gives off, as it falls to the ground state, it will give off a light with a certain amount of energy, only that specific amount. And we talked about with the Lyman series, you can go from 3 to 1, with 4 to 1, 5 to 1, and you can continue going up like that, those different energy levels. If you get past a certain point here, then basically the electron gets kicked out of the atom. It's got more energy, kinetic energy, moving than it does potential energy holding it together, and so it escapes. For the Balmer series, they go from the higher levels down to level 2. So there's only very specific levels of light given off. Okay. Another way that they show this is with a diagram that looks like this, with the protons in the center. There are only very specific models or levels where the electrons can be and so instead of having kind of a continuous place where they can be, it's only very specific spots. Okay. So we'll leave off with that for today. And we'll pick up here next time. So we've basically gotten through 3 models of the atom: the plum pudding model, the Rutherford model, which basically says that things are orbiting like a planet would, and then the Bohr model, where they're orbiting around the atom, but only at very specific orbit levels.